now we are going to continue working on this chapter, and the next thing is equipotential surfaces. Now, from the name here means equipotentials means uh, these surfaces have equal potential values. Okay, now I have actually um, just on Blackboard, you're gonna find a video like a YouTube how really to draw these equipotential surfaces. And just I'm gonna maybe jump into just part of it, and then you're gonna view the full video later. Let me show you here part that I was. Um,
Your lab TA will have already put the semiconducting paper in place with the conducting bars. Otherwise, you'll need to carefully punch holes in the paper for the next solid. As you'll see, we neglected to screw one of the nuts tight enough when we were constructing ours, and this led to later problems. With our two conducting strips screwed firmly in place, we connect the common input of the voltmeter to one of the strips using the alligator clip. Then connect the high voltage output of the voltage source to the other strip. Turn on the voltage source and adjust the output to approximately 10 volts using the coarse adjustment knob. Then use the red voltmeter probe to first check the voltage at the low end, which should read 0 volts, and then check the voltage at the high end. If the high end voltage is not exactly 10 volts, then turn the fine adjustment knob on the voltage source until it is 10 volts. Firmly touch the probe to the center line on the semiconducting paper. The reading should be approximately 5 volts. Notice here we got a reading somewhat less than 5 volts because we had not screwed one of the wing nuts tightly. Use the red probe to find a point on the paper near the 0 volt conductor with a voltage of precisely 2.0 volts. Once you've found that point, a white china marker may be used to mark the spot. Then locate another point nearby where the voltage is also 2.0 volts and mark this spot as well. Continue in this way until a number of points are located. The string of
right, then this is here.
Continue in this way, constructing equipotential lines for 3 volts, 4 volts, etc. through 8 volts. The holes in the paper must be along the x-axis at the points marked x equals plus or minus.
Right, then this is how we actually we did. For example, here I did show you that this one is 0 volt, this one is 0 volts, and this one is 5 volts, not 10. And then I did draw the 4. This is the red line. I did draw the 3 volt. Now, one thing that we need to know also that electric field lines are really perpendicular to these. Then I'm gonna come here for this one, draw the perpendicular. These are they gonna be the electric field lines, and they are always originating from the positive going to the negative. Here, this is really when we have an arrangement of, let's say, two charges, and these two charges, one of them is double the other. Like, for example, this one might be, okay. This one might be, let's say, a 5, which one is here? Sorry. This one Q1, and this is Q2. and they might be the same or different. It doesn't matter. But here we did use these two charges. One of them is negative, one of them is positive. Of course, the positive is the one that, the lines are really leaving. These are the electric field lines. And then when I draw perpendicular to these, I will have that equipotential surfaces. So far, we covered force equals K electric, Q1, Q2 over R squared, and this is a vector quantity. Then in order to, do a calculation, you need to deal with these as vectors. Electric field is going to be KQ over R squared. It's again a vector. Then we need to do a vector addition, and usually we are going to do adding by components. Electric potential, it's a scalar. You don't need actually to add as vectors. These are really numbers. The voltage, or we call it electric potential, can be calculated as K electric Q divided by R. When R is very large, we are going to infinity, the voltage is going to be 0, and we don't have a direction here. Just here I'm showing you, for example, if I have this arrangement, the difference between calculating electric field or voltage. This is a right triangle, and we did solve this one before. Then here I have charge, the one is positive, this one is negative, and the question is asking about calculating the electric field at this point here. And then I'm gonna say, if I will imagine there is a positive charge here, is going to be repelled, and therefore this is the direction of E1, and here this one is negative, then I will imagine a positive is going to be attracted, and therefore I need to calculate E1 as magnitude, E2 as magnitude, and then try to add these two vectors. I can say sum of E is going to be E1 plus E2, but that one is not going to be, just adding 5 plus 6, whatever, like the values are. You're going to, if you go back to when we covered that, you're going to find that we are going to add them by component. Whereas if you have a calculation of voltage, simply you're going to calculate what is really the voltage from charge 1, then this one is voltage from charge 1, and V2 is voltage from charge 2, and then you're gonna add them. And if one of them is, of course, negative, this means you're gonna have a negative value, and then you're gonna add them. Now here, showing you how we're gonna do this for one charge, and then showing you when we're gonna have two charges. 0.5 centimeter diameter plastic sphere used in a static electricity demonstration has a uniformly distributed 40.0 pico coulomb charge on its surface. What is its potential near its surface? Then this means it's at at the surface. Then V, it is KQ over R, and this is the K electric times the charge pico. It is 10 to the negative 12, and that is going to give us 144. Now, what if I have the same arrangement that I did show you before? This one is positive, this one is negative, and I have the famous triangle 3, 4, and of course this is 5. You can calculate it using C squared equals A squared plus B squared. Calculate the electric potential at point A. Therefore, I'm going to calculate first the voltage from this positive charge, which is KQ over R, 9 10 to the 9 40 10 to the negative 12 coulomb divided by 4 10 to the negative 2 meters, and that is going to be 9 volts. And also, I'm going to calculate the voltage or the electric potential from the negative 9 Q over R, and that is going to give me negative 7.2 volts. The total you're going to add, and then one of them is negative, one of one of them is positive, therefore they're going to subtract. All right? Then this is how we calculate the voltage. Now for this one here, we have an insulator that is charged, but it has non-uniform charge distribution. And then we're gonna sketch the equipotential surfaces, and then also we are going to have the electric field lines. Like, of course, here, since these are positives, these are the lines here. These are electric field lines, and then I can draw again, okay, perpendicular, okay, marks, and these they're gonna be the equipotential surfaces. Then this one is one of them, the red, and like complete like surface like this. And this one, let's say the green one. Okay, and I can, of course, draw more. I'm gonna stop here because I wanna cover the capacitor in another one so that I don't have a long video. Thank you.